Greetings, welcome back. Session 7, Part 2, Decision Trees. We are still in that discussion of how to make decision trees. There are different types of approaches. Some of them we are going to discuss. We have discussed one particular example in the previous recording. I would like to go and make it a little bit more formal and perhaps some of the equations are going to be elaborated now. So let's take a look at the screen and take a look. This is the decision tree, part 2 of session 7. With that in mind, decision tree is actually, it's really like a tree. So there is an attribute on the top. This is going to be considered the root node. And these are going to be considered the leaf node. The no, yes, this no, and this yes. They are kind of terminal nodes. You do have attributes in between that are going to have a question mark. You are going to test it. You're going to see whether that's going to be the way to go, the next step of your decision that you're going to make. And then you have basically branches. So in this example, which I'm going to show you the table in a moment, age, the question mark is that, is age going to be the top splitting node? Is the age going to be the first attribute you're going to put on top and first split the data, and then from then on you gain some information, and then the subnode you're going to split it again, gain another information, and eventually come to a leaf node, a terminal node. And under the age, we are going to take a look at the student. Are they a student? They are not, or they are. Credit rating, is this fair credit rating or excellent credit rating, and so on. Under the age, as you can see, these branches are actually related to the age. This no and yes are actually related to the student. This excellent and fair are related to the credit rating. This is the way we would like you to actually establish your decision tree. A node, these branches are related to the node, the top node that we have. The same goes here and the same goes here. And these are the decision-making nodes. And these are supposed to be the terminal nodes. In terms of shape, several people have chosen different types of shapes, square and circles and elliptic. So, but the concept is exactly the same. So all of them are trying to follow the same thing. So basically, we are going to eventually trace from age to the final. So the idea is to go from the root node until we get to the decision. And then we are going to see the weight of that decision. And obviously, for example, if the age is youth, noted as youth, and the student is noted as yes, then I would know what to do as my decision. If the age is going to be senior and the credit rating is going to be excellent, I know what the decision is going to be. So that's the way I'm going to actually read this tree. Actually, decision tree, although it has been with humanity for so long, maybe as long as the humans existed on the planet, it is formalized in 1980, almost 40 years ago, relatively new in terms of formalization, and or a little before that. But generally speaking, it's really in terms of equations and formalizing the process, it is really new. ID3 stands for iterative dichotomized tree. You don't have to know what that means. If you wanted, you can actually take a look at Ross Quinlan and take a look at the follow-up basically modifications. There has been many discussions, and even recently you can find publications for decision tree. We have classification and regression tree, or CART. We are going to refer to that in a moment. Okay, and what are the good thing about the decision tree? It is at the exploratory knowledge discovery, which is very nice. You really don't need to have domain knowledge, because the person who gave you the table had the domain knowledge, prepared the domain knowledge, knew what kind of parameters to basically extract on the field, and gave you the database. Now, if you're going to take that role and you're going to actually establish that Excel sheet or Excel file, then you need to know the domain, because of course What do you know about the columns or the attributes? You need to know the domain. It can handle multidimensional data, obviously, because it allows you to go through um, every attribute independently. You could potentially have 100 attributes. That means 100 dimensions. And these three representations make it easy to assimilate by human. Even human can do it. A piece of a paper, you're on your way. The learning and classification steps are simple and fast. Really it is. It's just a kind of fraction most of the time. There was an issue with the log. We are going to talk about log in a moment and see what we can do to replace it. Decision trees have good accuracy. Indeed, it is a good picture of the distributions of the outcome, the yeses and the noes and everything else. It is constructed as a top-down recursive divide and conquer manner, or categorical. For example, yes, no, red, green. All the training examples are going to be at the root, so that when you start at the very root, everything is going to be related to the root node. Examples are partitioned recursively based on selected attributes. So as you go to the follow-up attribute, you need to zoom into the data to particularly find that particular attribute. So the attribute, when you have it, depending on where you are, you need to actually view the entire data based on this attribute. So if it is root node, it means everything. If you come to a sub node, then you have already, you are actually making a split already. You have already split the data, and therefore your set needs to be a subset for the sub node. There are different way of representing this. For example, you could potentially have just A1, A2, A3. You could have red, green, and so on. You could have income, though all of those are categorical, low, medium, and high. You could potentially have a condition, a threshold, maybe 42,000, greater or less than that. Yes and no are perfectly fine, and that's the way we are going to consider that. It's not really basically difficult to establish that. As soon as you pick up the table, it should be very easy to go ahead and run with it. We are going to find the information per attribute. And in this case, we are going to look at the probability, and then we are going to go with the log of 2 of pi. We spoke of y log of 2, and we spoke of purity and impurity, and we said 50-50 is the time when confusion is high, and that's why we need to do 50-50 means 1/2. Log of 2 of 1/2 is -1. You multiply by minus, that becomes +1. The summation of pi, and that's going to be what you are going to get at the end of the day. And in this case, the p is actually per attribute, the class per attribute. So, for example, we have seen it in the previous example. I'm going to stress on that again in this recording. This C is outcome per attribute. So that's very important for us to consider. Then we have basically expected information, and the expected information is slightly modified. Take a look at the fact that info D already has the probability inside, already has the log of 2 of pi, but when we get here, it's going to be against the whole set. Once again, watch for D, watch for C. These two are actually two different items, and the numbers are going to be accordingly different. We are going to look at the gain, as we discussed last time. It's going to tell us how much information would be gained by branching on A. Information means it's going to help you to make a better decision. So if you go and you become, at some point you realize it is going to be 50-50, there is no information. You are still confused. 50-50, put your hand in the jug, in the jar, and then pick up a cookie. You never know it's going to be something you like or you dislike. So, but you like the gain to be the highest, meaning that you want at the end of the day, the entropy to approach 0. And as you approach 0, or as you gain information, what happens is that the subset, the subjar, I would say, is going to have more of the cookie that you already have made a decision whether you want to like it or dislike it. So that's what we want to do. This is an example. We are going to play this. This one is similar to the example we had the last time on playing golf. But this one, take a look at this. We have RID. RID is actually the entire table ID, the entity ID. This is an entity, and this is the ID. The ID, of course, is a perfect classifier. So if you say 8, I'm going to get you everything here. If you say 12, I'm going to get you everything here. So by just saying an ID, I'm all set. But here's the problem. When you have a new combination of age, income, student credit rating, and credit rating, you never know what the class is going to be. Is it going to be the buy computer, or is it going to be not to buy the computer? So even if you add another row, another tuple, I would say, where it is 15, and then you'll come up with an age, an income, and a student and credit rating, you don't have the outcome. You don't have the outcome. You want to find the outcome. That's why we are not going to go with the entity ID. Entity ID is not going to help you for feature classification. That doesn't work. So what are we going to do? We have the attribute of age, income, student credit rating, and class. Imagine you have gone to a Best Buy. Imagine you have gone to Walmart or Costco or any stores that you like to go. And I'm the cashier. I'm one of the people who are going to stand in the TV section, the electronic section, and you're going to approach me. And when you approach me, you want to see whether, which TV to buy. As a cashier, I'm going to see, I have many things in my disposal. I could potentially rely on my psychological assessment of who you are, the way you have dressed, the way you are walking, the way you are talking, but that's not reflected in this table. But then I'm going to say, I'm basically, with every TV I'm going to sell you, I'm going to make money, because my life, my salary depends on not only a basic salary, but also it depends on the commission. So when you come to me to buy a TV, I'm going to see who you are. Dressing, talking, walking, and even looking, the way you look at the items and how much time you spend. Are you a serious buyer, or are you just a window shopping, you know? But they have not been reflected in this table. This table has age, youth, middle age, senior. Income, high, medium, low. A student, no, yes, and no. Credit rating, fair, excellent, and that's it. And buy or not buy. You see, the reason I need to know whether you are serious in buying a TV is that I need to distribute my time appropriately. Time could potentially mean money to me. Not, of course, to everybody who is representing the electronic department. Of course, many people are going to spend equal time, whatever is necessary to whoever it is, for building a future relationship. So that's going to be a significant discussion point, right? But my idea is that, are you going to buy the computer or not? Are you going to buy the TV or not? So suppose that this is a computer section. And if you are going to buy the computer, I'm going to actually spend more time with you. I'm going to make you more comfortable at the moment. I want you to have the best product for your specific application. And I want you to be a happy customer so that you can come back to me. And if you're not going to buy a computer, I'm still going to spend time with you, but I'm going to wait for your questions to be asked first. So that's the type of approach. So it's very important for me to know whether you are interested to buy the computer or not. So this has been collected in the past 3 years. I have been working with Best Buy in the computer section. Now, someone comes in and that person is a young person. That person is a student. Credit rating is obviously fair, and income, I would say medium. So youth, medium, a student, yes. Credit rating, fair. So youth, medium, yes. Fair, I don't have it. Youth, medium, I don't have it. Youth, medium, no, doesn't work. Youth high doesn't work. So as you can see, this data just actually throw at the table doesn't exist. Youth, medium, yes, fair. It doesn't exist. If it existed, it would have been very easy to see what the decision is. The decision would be, take a look at that row, just search for that row and see what the response is, and voila, you got it. That's the classification already done. So if it is already in the table, it's very easy. What if it's not in the table? And you need to make a decision whether this person is going to buy it or not. So it is young, youth, medium, yes, a student, fair, credit rating. Does this person buy the computer or not? Now, I don't want to go into the detail, as we are going to go into the detail in a moment. You will see what it is. But the idea is this. I'm the person representing the computer section of Best Buy, for example, right? So I see that you're coming in. You seem to be just entering the university which is around the corner, by the way. And then I see you are a student and you're young and you need computer. All of your labs and assignments and everything you do, you need the computer. So if I take a look at my data, the data is going to confirm that majority of the students actually buy the computer. Not in this case, but generally speaking. If the data confirms that majority of the students are going to buy the computer, the very fact that being a student has highlighted that you are going to buy the computer tells me that being a student is sufficient. Start with a student, a splitting node, and then go into the age and worry about everything else. You know what I mean? That's the way it is. Because a student, 90% of the students are supposed to buy the computer. And the rest 10% possibly they are going to either borrow it from their siblings or father, or perhaps they already have it from high school, or they need to borrow it from the school. So the fact that you're a student, yes, this person very likely going to buy the computer. That becomes your root node. A student becomes, yes, the attribute of student becomes your root node. This is the way a human brain works. And we would like to formalize that decision-making process. Once again, I challenge you to consider that this is youth, this is medium, this is yes, a student, and this is fair. And I challenge you to tell me what my classification tells me. So C stands for class. C stands for class. So let's begin this process. I want to find information D, and information D in this case is going to be about the class itself. We have 9 tuples of class yes. If you count this, we have 14 rows, and if you count them, you're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 yeses, and obviously 14 minus 9, 5 no's. And then what we do, this is the way we do it. So 9 over 14, as a matter of fact, is a representative of the probability. So this is actually class division. So it's C in our formula in the previous pages. So this is 9 over 14. 9 over 14 is your probability. You don't have any other means. You just need to rely on the limited data that you have. And this is the way we are going to estimate the probability. 5 over 14, 5 over 14, and then you get 0.94. So that's going to be your class in general, 0.94 at the very end for the whole set, okay? Now, let's go back and begin a little bit of a process. Now, if you take a look at my new argument, the argument is this. The same table, we didn't change anything in the table. The age has youth, and the youth has 2 yes and 3 no's, okay? Youth has 2 yes and 3 no's. Just a table, we made a table. For category, we have middle age, and there are 4 yes and 0 no's. So if it is a middle age, you will know that it is a yes. And for the category senior, there are 3 yes and 2 no's. You count them. So per youth, you have 1, 2, and 3 and 4, and then 5. So you have 5 youths. So you have 2 and 3. So that's 5. And when you talk about middle age, you have 1 here, and 2 here, 4. When you add them, it has to be 4. And then you take a look at that. You map that to the class. The class is yes and no at the last column. The outcome, you map that to the target. You map that to the output. And then senior, you have senior here. So you have senior 2 and 3 here, and then 4 and 5. So it's going to be 3 and 2 has to be 5. An easy way to check. And the senior yeses are counted at the last column. So what is this going to be? I'm going to actually go for this, this specific attribute. It's going to be, first of all, we did have the 5 over 14. What is the 5 over 14? It is going to be the number of age you have. So what do you have? Youth you have. So you have 2 plus 3, that's 5. 5 over 14 is the whole table. It's the whole table. 14, as you remember, is my whole table. This is my D. This is not my C. This is my D at the moment. And then when you talk about the middle age, 4 and 0, that's 4 over 14. When you talk about senior, you have 3 plus 2, 5 over 14. That's my D. Now, if you take a look at my brackets, we are talking about C now, and C in respect to that age. So for example, this is 2 over 5. This is 2 over 5, 2 over 5, and then 3 over 5, 3 over 5. You see the difference between C and D? This one is 4 over 4, and then 0 over 4. And we basically, we didn't have to worry about that because that's going to give you 0 anyway, okay? There is nothing there. So the probability is going to be 1. So if you are middle age, according to the data, the probability is going to be 1 for yeses, and the probability is going to be 0 for no's. And then when we take a look at the senior, you're going to have 3 over 5. So this is 3 over 5. 2 and 3 is 5. 2 over 5. So please consider this fact that there are 2 different issues in my equation that you need to keep in mind. The equation is here. This is D, age over 14, age over 14, and basically middle age, youth over the number of youth, all of that over 14, the number of middle age, all of that over 14, the number of senior, all of that over 14, okay? So that's going to be my D, so I need you to keep that in mind. But then we are going to calculate the information, we are going to calculate in respect to the class itself. So it's going to be the yes versus that age category itself. So it's kind of a small set. So the D reflects to the whole set, the C reflects to the small set, okay? So this is what we got. We got 0.694 for the youth, middle age, and senior, and that's going to be the information for age. Now, if you remember, for the whole of the classes, we got 0.94, and for the age, we got 0.694. When you subtract, you're going to get the gain. The gain is 0.246. So you're going to scratch your head and you say, should I have the first splitting node on age? That's what you did, 0.246, that's the amount of information you're going to gain. Then you're going to repeat the very same process. You're going to say, should I have my splitting node on income? And you have, under the income, you have sub items that you need to consider. Remember, we have a D versus the whole table, and then we have the C versus the sub table, sub elements. And then you're going to subtract once again from the top node. The top node, it doesn't have any attribute. The top node, the whole set, the class, does not have any attribute. It is not based on the attribute. It is actually based on the last column, this column. This has nothing to do with these columns. It has everything to do with the last column. But we are trying to see whether age is going to be a splitting node, income, a student, and credit rating. And now when we subtract them and we calculate and subtract them, we see 0.246, 0.029, 0.151, 0.048. Which one gives you the maximum information gain? And the highest, the maximum information gain is actually achieved by the age. So what do you say? You're going to say, listen, I'm going to start my decision tree from the splitting node, and the root node is going to be age, okay? So, and then that's what possibly, I hope that's the way it is. in my original tree, the example we started from. So if you take a look at my example, we said age. And after age is out of the picture, you know it is going to be the root node. You're going to go into the student and repeat the process. You're going to do the grading rating and repeat the process. In this case, the beauty is that a student is going to be possibly basically yes and no, because that's what the table says. Credit rating is going to be excellent and fair. And then you're going to see whether there is any other sub node that you need to consider. And then you consider that until you get the decision tree completed, okay? So that's the idea, and I hope with this second example, the picture of information gain is very clear. And then keep in mind that, again, in terms of clarity, in making decisions, in terms of purity and impurity, if you're talking about national ID, that's what we said. If you're talking about national ID, obviously everyone is going to have a unique national ID. And if you have unique national ID, this is going to be pure. Every subset, which is supposed to be under the national ID, is going to be the terminal node. You don't have anything under the myself after my national ID is actually projected. You know all about me. Everything is going to be there. So that's the important thing. So you really, it's easy to make a decision when the purity is maximum 100% or impurity is actually 0. Reflecting on the cookie example, for example, right? Slowly they try to actually simplify the process. As you can see, we have removed the PI, and then we are actually now considering the D, the class itself. And let's actually do this gain ratio. This is the second approach. The first approach, we talked about probability and everything else. The second approach, we are talking about the gain ratio. Yes, you can repeat the decision tree with different approach and calculation. So keep that in mind. Now we are talking about the different one. We don't want to talk about the P. Take a look at, and then the gain versus the split info is going to be my gain ratio. For us to understand that, let's begin with an example. The very same example, test on income. It splits the data into 3 partitions, low, medium, high, containing 4, 6, and 4 tuples. So low has 4 tuples, medium has 6 tuples, high has 4 tuples. Tuples means a row in your Excel sheet. So if you calculate that, what do you get? You're going to, you see, we are not talking about yeses and nos anymore. We are not talking about a mapping of the column versus the mapping of the attribute column versus the last column. We are not counting yes and no's anymore. So take a look at this. I'm going to say 4 versus 14, 414, 6 over 14, 414, and I'm going to calculate that. That's going to be 1.557. And 1.557, then you have, you're going to calculate the gain. The gain of income is separate. You remember the gain of income you have already calculated before, and then you're going to have the gain ratio is going to be 0.029 divided by 1.557. And the reason we want to do this is that we don't want to be dealing with this complexity of finding the gain all the time. We would potentially want to simplify the process. So 0.019, and you could potentially find the one that has the maximum ratio. So if this is bigger and bigger and bigger, obviously this one is going to be bigger and bigger and bigger, right? So that's the way we are going to do it. A slightly modified calculation, and then we are going to make it even easier this time. This time, the fact that the log function exists actually has a computational execution time attached to it. Log functions are inherently complex, and they take time to calculate. Depends on the fractions, depends on the accuracy you have. Of course, we have supercomputers now, but imagine if you're dealing with millions of rows and perhaps hundreds of columns, then this is going to be quite challenging to calculate the log fund. So the way we are going to do it, we're going to talk about the, we are going to actually exclude the log. And then potentially we are going to have a better equation, which is called Gini. Gini index is used in correlation and regression trees. So that's a very specific tree. And then we want to, let's take a look at an example. So if income has 3 possible values, you have low, medium, and high. Then the possible subsets are going to be all 3 of them at the same time, low and medium only, 2, low and high only, 2, medium and high only, 2, and then low as in 1, medium as in 1, high as in 1, and then perhaps none. So we want to see which one to calculate. So take a look at this. Compute a weighted sum of impurity of each resulting partition. I'm going to showcase this in an example. So we are going to calculate the Gini A, and then we're going to calculate the difference. Once again, similar to gain that we have discussed in the past. Now, in this example, remember we don't have log anymore. It's going to be 1 minus the summations of p to the power of 2. And we are going to assume that the p is going to be a simple fraction. And then 9 tuple belongs to the class by yes, and 5 belongs to the class no. So the original Gini of the target column of the outcome column, this one. So the Gini of the outcome column is going to be 0.459. And the way we calculated it without having any log, and then 1 minus the summation in mind, we get 9 over 14, 5 over 14, and so on. So that's going to be the Gini of the target column. Now I need to calculate the Gini of, for example, I believe income. So what we are going to do, we are going to calculate the income. Let's start with the attribute income. Let's consider low and medium. It would result in 10 tuples in partition D1, satisfying the condition income belonging to low and medium. How do we calculate that? So income, low and medium. So low, 1. So medium, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So if I say low and medium, I'm going to combine them. I'm going to add them. If I say low, medium, and high, it's going to be 14. If I say high only, 1, 2, 3, and 4. If I say medium only, 1, 2, 3, 4, 5, 6. That's the way we are going to do that. As you can see, this is extremely easy. And even someone who is in elementary school should be able to count them. It's a count, right? Now, let's calculate the Gini of the low and medium. The Gini of low and medium, so we have 10 over 14 and then 4 over 14. That's the target. So we are actually mapping it to the target class, to the target column, to the outcome column. So it is 10 because you have 10 of medium and low together and 4 of high only. So that's the 10 over 14 and 4 over 14. How do I calculate Gini of D1? Gini of D1, I'm going to actually say how many yeses I get and how many no's I'm going to get. Now, if you take a look at the, we had 10, right? So let's have an eye on 10. You have 1 yes, that's 1. Let's take a look at it. It's worth being patient. 1 yes, 2 yes, that's 2. This is no, I don't want that. This is a yes, that's 3. That's 3. This is another low, and that's a yes, that's 4. Then medium and medium and medium, there are 3 yeses, that's 7. So now I'm mapping the component, the low and medium case of the income onto the target column. So it's going to be 7 over 10, and the remaining, of course, supposed to be 3 over 10, right? This total is supposed to be 7 plus 3. You can actually see it if you wanted to. Low, no, that's 1. And then medium, no, that's another 1. And medium, no, that's another 1. Okay, so that's it. Now, when we get to D2, what is D2? D2 is going to be the complementary parts of low and medium. And D2 is going to be the high case. The high case, I have 1 high here, 1 high here, one high here, 3 highs, and 1 high here. So I have 4 highs. So low and medium in one basket, high is another basket, okay? So the highs, I have 2 no's and 1 yes and 1 yes, 2 and 2. So it's going to be 2 over 4, 2 over 4. That's the way I'm going to calculate the Gini. So once again, please keep in mind, the factor behind is overall. So the basket of low and medium compared to the whole set. And then inside each set, you're going to map it to yes and no, the target column, okay? And then you calculate 0.443. That's the way you can do it. And keep in mind that the Gini of low and medium is exactly the same as Gini as high, because you're always looking at the complementary. If you say high first, obviously you need to consider the low and medium anyway. So it's low and medium, high, high, and low and medium. So these two are actually the same. So this is going to be the Gini index for low and medium, okay? And then when you calculate that, we have done it already, for example, and we got the Gini index values of 0.367 and 0.429. And the best split is going to be on the age. So I hope the numbers are correctly calculated. It's 0.375. Okay. So please double check the numbers to make sure that the numbers are correct. Now, 0.459 minus 0.357, that's going to be 0.102. Therefore, for the youth and senior, the results with maximum reduction in the impurity. So that's the way we are going to do it. Keep in mind, the only reason we want to use Gini is because we want to avoid the complexity of log. And of course, it found its own application, which is correlation and regression trees. That's very nice. I would encourage you to read this in details. This is the last slide before we go to the third part. Information gain, it is biased toward multi-valued attributes. Obviously, if you have more attributes, it's going to be quite challenging. Gain ratio prefers unbalanced splits in which one partition may be much smaller than the other. And the Gini index has bias to multi-valued attributes, has issue with number of classes. When the number of classes is large, tends to favor tests that result in equal sized partition and purity in both partition. You could potentially examine these statements and you take them away with you, because at some point in an interview, maybe they ask you, what's the pros and cons of information gain? What's the pros and cons of entropy analysis? What's the cons and pros of Gini calculation? Do that kind of a search on the internet, or perhaps go back to the table I just provided to you, and then you're going to basically try an attempt. For example, make it equal size, make it a smaller value in the table, and then see what happens. Different attributes, higher attributes, fewer attributes. Inside each attribute, make it perhaps just 2 or 3 values instead of 10 values, and see what happens. Just think about it and then come up with the pros and cons of each one of these techniques. None of them is going to be perfect. In data science, like any human, we are going to make mistakes sometime. And in the data science, as a human, our mistake is going to be mapped onto the computer. Remember the separation of computer and human being. If we make a mistake in the coding process, the computer is going to make that mistake anyway. Although the computer says I was perfect, I just followed your orders, and you can't blame me because you told me what to do, I did it. That's what the computer says. But generally speaking, the human thought process is going to be mapped into the computer process. With that being said, we finish the part 2, and we will go to part 3 in the next recording. Thank you. Stay tuned.